Hello everyone. In this video, we will try to learn why can't two electrons be in the same state. The answer to this question is Pauli's exclusion principle. What does Pauli's exclusion principle says? It says that no two electrons can have exactly the same set of four quantum numbers n, l, ml and ms. N being principal energy level, L being orbital angular momentum, ml is magnetic quantum number specifying Lz, and ms is spin projection quantum number specifying Sz. But saying simply that Pauli says they can't isn't really any explanation, right? There should be some base for this principle, right? So to understand that better, let's imagine two electrons. We will consider two electrons. Now electron 1 and electron 2. Electrons are identical particles. That means there is no way you can differentiate between electron 1 and electron 2, right? Okay. Now let's say we have two one particle states, psi A and psi B. These two states electrons can occupy, right? Now these two electrons come together in a system. They are forming a system. So using ordinary product state construction, we can say that electron 1 can reside in psi A and electron 2 can reside in psi B, or electron 1 can reside in state B and electron 2 can reside in psi A. Keep in mind that this 1 and 2 are the labels which we have given for the mathematical convenience. There's no way you can distinguish between these two, right? So these two assignments, this and this, these two assignments are physically indistinguishable. So their combined state, how can I write their combined state? Their combined state can simply be a linear combination of these two states. So let me write the combined state. Psi of 1, 2. What is this? This is a combined state of electron 1 and 2. Some coefficient psi A 1, psi B 2 plus another coefficient psi B1, psi A 2. Okay. So what is psi 1, 2? It's a combined state of 1 and 2. 1 and 2 are the labels which we have given to our electrons. Now let's say we are exchanging 1 and 2. Okay. So we have exchanged these electrons. Now what would be the new state? The new state would be psi 2, 1. After exchange, this is the new state. Let's number this equation as 1, and psi 2, 1 would be simply, we have exchanged the electrons now, right? So in psi A we have 2 and in psi B we have 1. Okay, let's number this equation as 2. If the question is about classical mechanics, then there's no way these two states can be separate. Psi 1, 2 should be equal to psi 2, 1. But quantum mechanics gives us two possibilities, right? So upon exchange, we have either psi 2, 1 is equal to psi 1, 2, or psi 2 1 upon exchange, the wave function is equal to negative of minus of psi 1 2. So if this is true, you're going to get symmetric wave function, and if this is true, you're going to get antisymmetric wave function. The question is, in these two, which one are you going to choose for electron? So for this, let's go into spin statistic theorem. So what does spin statistic theorem tell us? It tells us that when the particle is having spin half, alright, so the particles with half integral spin obey Fermi-Dirac statistics, and their many particle wave functions are antisymmetric under exchange. So their wave function should be antisymmetric under exchange. Hence, what we understand here is psi 2 1 should be equal to minus of psi 1 2. Now when we take this condition and we try to impose this condition on equation 1 and 2, which we have written here, we get to know about the coefficient. What we understand is, upon solving, b must be equal to minus a, then only this would be true. Okay, so now simply I can write psi 1 2 as a, I am taking out as common, psi a of 1, in psi b we have 2, and in psi b we have 1, and psi a we have 2. Right. Hope you have understood this step, right? B is equals to minus a, I am substituting in psi 1 2. This is our equation number 1. Okay, so a is the normalization constant. Normalization coefficient. So when you solve normalization condition, you try to find a, and then what you get is a is 1 by root 2. I'm not paying more attention on this because our aim is to see why electrons can't occupy the same state. Okay, now we'll come to Pauli's exclusion principle. Okay, so for that, what I'll assume is, I'll assume that both the electrons 1 and 2 are trying to occupy exactly the same one particle state. Okay, same one particle state. So what I'm trying to assume, I'm assuming that electron 1 and 2 are occupying the same one particle state, and that one particle state is psi. So now how my equation psi 1 2 will change? So let's say that same one particle state is psi, which is nothing but psi a, which is equal to psi b. So now I can reconstruct psi 1 2 as 1 by root 2 psi of 1 psi of 2 minus psi of 1 psi of 2. Right. So what is this? This is 0. So what do we understand from this? If wave function itself is 0, its probability amplitude also should be 0. Correct? So psi 1 2, magnitude of psi 1 2 square, which is nothing but probability amplitude, should also be equal to 0. So the probability density is 0 everywhere. In other words, that proposed 2 electron state, the psi which I have proposed here, this psi which I have proposed here, does not exist, because its wave function is 0, probability amplitude also is 0. So it's not that two electrons aren't allowed to be together. The quantum state itself disappears when we try to put two identical fermions into the same state. Okay, electrons are fermions. Okay, so hope this episode is clear to you.